Now that we know what the Hessian matrix is and how to calculate it, we can use that to write down our formula for what the Taylor approximation is. The constant Taylor approximation, just like before, looks like just the value of our function. The linear Taylor approximation is the one we've written down many, many times earlier in this class. F of x is pretty close to f of a plus df of a times x minus a. So we think about this as being like f prime of a times x minus a from single variable calculus, except we convert it into Jacobian and a matrix multiplication. The formula for the quadratic approximation takes that, so we've got our constant part and our linear part, and then throws on this new bit here involving the Hessian. We've got the Hessian as a square matrix in the middle, and rather than multiplying it by x minus a squared, which doesn't make any sense because we can't multiply a column vector by itself, what we do is we multiply it on the right by x minus a, and we multiply it on the left by x minus a transpose, and then we divide the whole thing by 2. That's the analog of the single variable calculus formula, f double prime of a times x minus a squared. We just replace the second derivative with the Hessian, and we convert this squaring part into a column vector on the right and a row vector on the left. So here's an example of computing the second Taylor approximation of this function. F of xy is xy squared. Near the point, xy is 1, 3. So the first thing we need to do is we need to compute df. We need to compute the Jacobian matrix by taking the x derivative is y squared, and the y derivative is 2xy. From that, we can then calculate the Hessian matrix. The Hessian, in its first column, we're putting the derivatives of y squared with respect to x, that's 0, and the derivative of y squared with respect to y, that's 2y. Then in the next one, we're putting the derivatives of 2xy with respect to x, that's 2y, and the derivative of 2xy with respect to y, that's 2x. So that's our Hessian matrix. But we don't want just the Jacobian and just the Hessian. We want them at this particular point, 3, 1. So we plug in x equals 3 and y equals 1 into this formula here. When I plug in y equals 1 into y squared, I get 1. And when I plug in x equals 3 and y equals 1 into 2xy, I get 6. So that's my Jacobian matrix. For the Hessian, I plug in x equals 3 and y equals 1, and I get the matrix 0, 2, 2, 6. And so for the whole thing, I get f of xy, which is 3, plus my Jacobian matrix times the column vector x minus 3 minus y minus 1, plus 1/2 of this row vector, x minus 3 minus y minus 1, times the Hessian matrix times this column vector. And so if I was to simplify this out a little bit by getting rid of the matrix multiplication, I would get 3 plus 1 times x minus 3 plus 6 times y minus 1 plus 1/2 of 0 times x minus 3 squared plus 2 times x minus 3 times y minus 1 plus 2 times x minus 3 times y minus 1 plus 6 times y minus 1 squared. So that is what I would get if I expanded out this whole matrix multiplication. And then I could simplify this pretty dramatically. I could get rid of the part that involved 0, and I could collect together terms. And so the whole thing would give me 3 plus x minus 3 plus 6 times y minus 1 plus 2 x minus 3 y minus 1 plus 3 times y minus 1 squared, like so. So this is the quadratic Taylor approximation to this function, near x equals 3 and y equals 1. I'm going to leave it like this. You could try to simplify a little bit more by actually multiplying out the x's and y's. If I leave it like this, then I know that's kind of in terms of how far away a point is from x equals 3 and how far a point is from y equals 1. So a couple of issues that come up with doing this quadratic Taylor approximation that are very common is it's very, very common to forget the factor of 1/2. when you throw in the Hessian. And don't also forget to plug in that you want the Jacobian and Hessian at a particular point. You don't just want to write down them in general. And usually you don't want to just leave it in matrix form. You want to expand it out a little bit unless you're specifically not asked to.